How to design a heat exchanger, identify applications, temperature, heat loads, mass flow rate, decide on construction type. 3. Evaluate LMTD, QNF. 4. Determine dimensions. 5. Evaluate heat transfer coefficient on hot side. 6. Evaluate heat transfer coefficient on cold side. 7. Determine overall heat transfer coefficient. 8. Determine dimensions. Iterate. 9. Check power consumption.
Okay, so now we can come over here and calculate the required number of baffles. Then we'll evaluate the heat transfer pick. So we just, based on our experience, we'll decide, okay, in this particular case, I said, we're going to use a shell and tube heat exchanger. And I've drawn that here, just a dot. The type yet. In this case, we just have a heat exchanger where we have cold flow coming in, hot flow coming in. And so in this particular case, it's been specified for us. The inlet temperature of the cold flow is 35 degrees. The outlet temperature is 120 degrees Celsius. The inlet temperature of the hot flow is 300 degrees Celsius. And the outlet temperature of the hot flow needs to be 150 degrees. So we just, based on our experience, we'll decide, okay, in this particular case, I said, we're going to, we have kilogram K. So we can plug that in. For our cold flow, we had 2.8 kilograms per second. And our temperature out was 120, temperature in was 35. And we get a Q of 998,410 joules per second, although we normally express this in kilowatts, so that would be 998.2 would be T hot out minus T cold in. Okay, and over here on the vertical axis, we have our correction factor F. On the horizontal axis, we have what's called P. And you can see it's P, it's a little formula is given here. P is equal to little t out minus little t in over big T in minus little t in. And then over here, these pink lines or magenta lines, we have R, and that's given by big T in minus big T out over little t out minus T in. So we need to calculate R and P so that we can use that graph. So I've done that on the board over here. And it says on the table, which you couldn't see here, but if you look in the notes I gave you, it's on there. The little t's are the tube side flow. The temperature, pick the number. Okay, the flow is coming down in this direction like this. So we have flow coming into the tubes, that's the tube side flow, in the vertical direction they're aligned, and the horizontal direction they're aligned. You can see this row is off. Okay, and the restrictions on this correlation, the number of rows, NL is the number of rows. The number of rows has to be greater than 10. The Reynolds number, based on the maximum velocity, has to be greater than 2,000 or less than 40,000, and the Prandtl number has to be greater than or equal to 0.6. For the staggered arrangement, Vmax could occur through either A1 over or A2, whichever is smaller. So let me go over here and I'll demonstrate what I'm talking about. We have the flow coming in, and you can see this would be A1 here. It could go through here, but it's going to make a turn here and go up through A2 right in here. Now when it makes the turn, if you notice, the flow comes in, it goes through this one area, but when it makes the turn, it goes through A2 over here and another A2 over here. Okay, so we have flow through A1, which is right here. Then it bifurcates. Part of it goes over here, part of it goes over here. And we have to take that into consideration. The way we do that is, if we look at the board, we have from continuity, V1A1 equals V2 times 2A2, because it has the relation that I gave you. You know that we have flow going through the tubes like this. design procedure, and we just have, we need the mean velocity. Okay, now we're ready to move inside. .438. So we add them together, and then we take the inverse, and we get the overall heat transfer coefficient is 1398 watts per meter squared K.
Overall heat transfer coefficient. That's important.
Okay, now that we have that, we're now ready to determine the dimensions, and the dimension would be the log mean temperature. Okay, so we're going to go through the two between log mean temperature difference. We got the heat rate, and since it's a shell and tube,